Okay, today we're going to be working on a little bit of circles. So we did this last week and we did a basic intro. So last week it was basically really simple, like stuff like area, stuff like sectors, arc length. So we're going to get into this, but a little bit deeper. But first, let's start with a review, okay? So here are some of the basics. So every circle is a 2D shape with a center, where every point on the edge of the circle is the same distance away from that center, right? So if we have 3 lines here, we see that every point or every line here from the center of the circle to the edge of the circle should be the same length. And if I move them over here, by this little animation, we can see that, yes, they are roughly the same length. And this is what we call the radius, or normally we just say r in equations. So what's next? Well, we also have something called the diameter, where the diameter is 2 times the radius, and it's just the radius stacked on top of each other, right? And we'll notice, if I go back, that this diameter actually cuts the circle in half. And it actually does this for any circle, not just this one, okay? And the last one is this outer ring. And this is called the circumference, right? So that's the length of the edge of the circle. And basically, for any circle, their circumference is always dependent on its diameter. So there's a relationship between the diameter of the circle and the circumference of the circle, right? So here's an example. I have this little animation and it plays and it put down 3 diameters. And we can see that roughly this covers the set circumference. So does that mean that the circumference is 3 times the diameter? Well, yes and no. Yes, because yeah, it fits in, but we also have this little spot here, right? And this spot, we don't really know what this part is. So all we know is that the circumference is a little more than 3 times the diameter. Now we actually have a special number for this situation. So does anyone know what the actual, like the perfect amount of diameters in a circumference is? There's a specific word that we use that I taught last time. Does anyone know this? You can type it out in the chat or in mute. No? Okay, no problem. So this is actually something we called pi, right? And so this is just how you say it. The actual symbol is something that looks like this. And with this, basically, this represents a number. And that number is about 3.1415. And it goes on and on and on. So this is actually an infinite number. It never stops. And that's why we use this symbol pi to represent it, because we can't just write this down every single time we want to say it, right? So the circumference is not actually 3 times the diameter. It's actually pi times the diameter. And that makes a lot of sense because pi is 3.14. And this 14 is a little more than 3, which actually perfectly covers this part. So this part is actually 1.45. Okay. So this is pretty basic, should be not too complicated. So let's move on. So we have a couple relationships that we see with pi. And this is number 1, what I just explored. The circumference is the diameter times pi, right? So pretty self-explanatory. Now, we also know that the diameter is 2 times the radius. Remember, d equals 2r, right? Because in a circle, given 1 radius, if we project this radius onto the other side, then this whole thing is a diameter. So we can say that the diameter is 2 times the radius. And so replacing 2 radius with diameter, we get the circumference is 2 times the radius times pi. And the last one that we have is the area of the circle. And that, there's actually a special proof for this, but we're not going to go over that. I'll just state it real quick. It is pi times the radius, or in other words, pi r squared. And we also learned this last time. So let's start off with some review problems, right? So here we have a circle where the radius is 2. And how would I go about finding the area of the circle? Well, very simple, right? I only need to know the radius, and that's exactly what I have. So I can say that the area of the circle, which I'll represent with A, equals pi times radius, which is 2, times radius. And 2 times 2 is 4. So I would say that the area is 4 pi. Now, what you could do is you could split up pi, and instead of writing pi, you could go 3.1415 down, all the way down, and you could put this in a calculator. So on a normal calculator, there would actually be a button with this symbol on it, and if you press that, then it'll just give you this number. But since this is way too complicated, mathematically, usually just saying 4 pi is acceptable. So let's try this next problem. So here we have the diameter, and that equals 10, right? So I'm going to give you guys a minute, and I want you guys to try figuring out the area of the circle. Remember that the diameter is 2 times the radius. So give you guys a minute. Try finding the area of this second circle here. Okay, does anyone know what the area of the circle is? If you do, feel free to type it in the chat. I'll go over it in a second. Okay, so the diameter is 10, right? And we want to find the area. And in order to find the area, we need the radius. Okay, so you said, I don't get it, and that's completely fine. So the whole concept here is I'm trying to find the area of the circle. And this might be a little bit confusing, and I apologize if you didn't come to last week's class. So I'll re-explain this. So given a circle, so I'm here, I want to find the area of it, right? So everything that's inside here. And what I know from this is I know the radius. So this line here. So if I move over to this circle, I know the radius, and this radius is 2. And I'm trying to find the whole circle. So the formula for how to find the area of the circle is just A equals R times pi, right? And so A equals R squared pi. Now, we have something very similar here, but instead of a radius, we have a diameter. And we know that the diameter is 2 times the radius. And so basically what I can say is I can move this 2 over, right? Divide both sides by 2, and I get half of a diameter equals the radius. And so if I know that the diameter is 10, what is half of 10? 5, right? And so I get the radius is 5. And that makes a lot of sense because this is the radius right here. So that's half of 10. And so to continue on and find the area, all we have to do is plug that back into the equation. So A equals pi times 5 times 5. And so I can multiply these 5s together and get 25 pi. And that's the area of the circle. So does that make more sense? Well, if you ever have another question, you can. Okay, good. So if you guys have questions, feel free to ask. But we're gonna move on. And so now that we've explored the radius, we're gonna go into something called the arc length, right? So I'm pretty sure you guys also explored this last week, but the arc length is just a section of the circumference. So the circumference, if you remember, is this whole thing that goes all the way around. And the arc length is just a little section of it, or a fraction of it, that we say. And so here, I've put down a fraction, and we'd say that the arc length over the circumference, and the reason why we need this fraction is because it actually has a relationship between what comes next, and that is the sector area. So a sector is just the area underneath this arc. So if the arc goes from here to here, all we have to do is extend that down back into the center, extend that down into the center, and find the area over here. And that is the sector area. And basically what this fraction equaling this fraction means is it means that the percentage that this arc length covers over the circumference is the same percentage of the sector area over the entire area of the circle. Now, what does that mean? For example, if I said that the arc length is 2, right? So if my arc length here, this green line, is 2, and the circumference is, for example, 10, so 10, then the fraction I could simplify down to 1 over 5. And basically, that means that 5 arc lengths can fit in one circumference, right? Because the arc length is 1/5 of the circumference. But now that I know this, I also know that the sector area, which is underneath this arc, is the same fraction here to the area of the circle. So I know that the sector area is also 1/5 of the area of the circle. So I know that 5 of these areas can actually fit in this circle. All right, and we have one last one, and that is the central angle. Okay, so what the central angle is you just take this sector and the place underneath this arc, and you draw your angle here, right, between the two radii. And basically, this also fits in with the same ratio. So again, if I said that this was 1/5, then I would know that the central angle is 1/5 of 360. Now, why 360? Well, because 360 is how many degrees are in a circle, right? If I go from here and I go all the way around, I know that is 360 degrees. So that is the whole circle. And since this is 1/5, this is 1/5, then I know that the central angle is 1/5 of 360. Okay, so that was a lot of information. Do you guys have any questions? Anything I should clarify before we move on?
I'm very confused.
Okay. So, which part are you confused about? Are you confused about like these parts individually? Do you understand like what
The
arc length is?
sector
Do you understand?
area.
Okay, the sector area. Okay. So the sector area is this area inside here, right? So for example, if I draw another circle and I have a different arc, so let's say this, all of this is my arc, right? This side. And I can draw 2 radii going up to that arc. So basically what the sector is, it's the whole area inside of what I've just drawn here. So that's all the area. And basically, this
So
entire
that's
area,
sector area.
yes, it's the sector area is just this part. And basically what this fraction means is that the sector area is the same percentage of the circle. So like, for example, what it looks like is it looks like the sector area covers about, I'd say like 25% of the entire circle, right? Because the entire circle is this whole part. And I would say that this sector covers about 25%. And if I know that this sector covers 25%, then I also know that this arc out here is 25% of the entire circumference, right? So there's a relationship. So that's what arc length over circumference equals sector area over the area of the circle means. And so going back to this main circle here, since we know that the sector area is the same percentage of the entire circle as the arc length is to the entire circumference, and then we also have this central angle here, we know that the central angle should also be the same percent to the entire circle, which is 360 degrees. Does that make sense? Yeah, I hope so. So don't worry, we're gonna actually do a problem with this now. So Hopefully this clarifies it a bit. So, first of all, we have what's given to us is a radius, right? The radius length. And what's given to us is also this angle here, which is, this is just theta. If think of it like a variable like x, we usually use this symbol, which is like a 0 with a line in between. We use it to describe an angle usually, but in this case, you can just think of it like a variable like x, right? So we know that this angle is 135, and we know that the radius is 4. And basically, what I want us to do is to find the area of the sector, right? And I've put down these fractions down here, these relationships, to help us out a bit. So we have this central angle. So first I'm identifying.
Is it just 1/3? Wait,
At
no,
1/3?
never mind. That's not 1/3.
You might be correct, actually. Well, let's see. Let's follow the procedure, right? So here's what we have. We have the angle, right? So we have this. We have 360 degrees because we know that every circle has an angle of 360 degrees. And then we have, what else? The radius. Now, what can we find with the radius? Well, with the radius, since we're trying to find the sector area, and in order to do this, we need the area of the circle, we have to use the formula for the area of the circle, right? So the area of the circle in this case is just radius times the radius times pi, remember? And that would just be 4 times 4 times pi, which is 16 over pi. So according to this fraction, the area that we want to find, so this sector area, right, this blue part, that over 16 pi, which is the area of the circle, should be equal to the central angle, which is 135 degrees, right? This is what we have here, over 360 degrees. Okay, so how do we solve this? Well, this is just algebra now, right? We're trying to solve for a. So what we could do here is actually we could simplify this fraction. And if we simplify it, you could use your calculator or something, but I'll just say it for now. This should be about 3 over, it should be 3 over 5. Here, I'm going to check it with a calculator because I want to be sure. Okay, not quite. Okay. So actually, let's do this. Let's do this step by step. I don't want to skip over steps. All right. Let's just divide or like simplify this fraction. All right. So what goes into this fraction is, well, how I would do this is I would go here and I would divide by numbers that fit into both of these, right? So I know that 45 fits into 135 and it fits into it about 5 times, or no, 3 times, yes. So the top is 3, and if we simplify the fraction, the bottom of the fraction, all we do is 360 divided by 45, and this fits into here about 8 times. So it should be 3 over 8. So all this was just to find the percentage or the fraction of the central angle to 360. So 135 over 360 is 3 over 8. And so a over 16 pi should also match this fraction, right? So how do we isolate 8 to find a? So if we have this and this, remember algebra, all we have to do is multiply both sides by 16 pi. So I can multiply this by 16 pi, which would cancel this bottom here. And then I can multiply this. Yes?
Is it just 6/16?
6/16? Let's see. So if I write this down, right, I have 16 pi, and I can simplify this because this is 8, and 8 goes into 16, so I can cancel this out, and this is 2, and so we have 6 pi. So not quite, but there is a 6, and we still have our pi here. So this is actually the area of the sector, okay? So just to reiterate, what did we do here? We were given the radius, we were given the angle, and we looked at down here, we need to find the sector area, right? So all we did was we found the area of the circle and we found the fraction of the central angle over 360. So the area turned out to be 16 pi and the fraction turned out to be 3 over 8. And so all we did was we solved a over 16 pi equals 3 over 8. And we found that the area of the sector is 6 pi. Okay, now don't worry, we have another problem here, and I'll go over this one too. And this one is a little bit different because we're actually given, right? We're given this arc length here, and we're given that it is 2 pi. And so the goal is to find, again, the sector area. So can you guys try or just identify which parts of this fraction we would need to use? For example, would I need to use the arc length over the circumference? Would I need the central angle? Which ones do you think we need to use? Any ideas? No? Okay. Well, here, I stated that this is the arc length, right? So we actually don't have to think much about this. We already have the arc length. And so we'll use the arc length because it's given to us. Now, this is the harder part because we don't actually have anything to compare it to right now, right? But let's just write down the fraction for now. So arc length over circumference. Our arc length is 2 pi, and our circumference, or C, is 12 pi. And I can simplify this down further, right? Divide top and bottom by 2, and that's 1 over 6. And the pi's cancel out as well because I can divide top and bottom by pi. So we know that 6 of these arc lengths can fit into one circumference. Now, how do we get the sector area? Well, in order to get this, we need the area of the circle, right? And in order to get the area of the circle, we need the radius, right? Now, how do we find r? Well, we have the circumference, right? And remember the relationship. The circumference equals the diameter times pi, because about 3.1 diameters fit into one circumference, right? We explored this on the second slide today, I think. And we know that the diameter is 2 pi. So we can say that this is 2r pi, because 2 radii go inside of a diameter. And now that I have this, all I have to do is solve for r, because I know the circumference. The circumference is 12 pi. So I know that 12 pi equals 2r pi. So the radius, all I have to do is divide both sides by 2. So divide this side by 2, the 2 goes away. Divide this side by 2, I get 6, or 6 pi. And I have this pi left over here, so I'm going to put that here. And now, to isolate r further, all we have to do is divide both sides by pi. So that's gone, and we know that r equals 6. So the radius right here equals 6. Okay, now that we have that, we can go on to finding the area of the circle, right? So if we know that r equals 6, a must equal 6 times pi, because the area is radius times pi, which is 36 pi. So the entire area of the circle is 36 pi over the sector area, which is what we're trying to find. So I'm calling that A. And then that equals the arc length of the circumference, which we found earlier. That's 2 pi over 12 pi, which is 1 over 6. And now all we have to do is isolate A, right? So what is A? Well, A is just this, and then I can multiply both sides by 36 pi, which will cancel out this, and I'll put that here. And then 36 pi over 6, 36 divided by 6 is just 6 pi. So the area of the sector in here is 6 pi. Okay, so now do you guys have any questions? Okay, seems pretty good then. All right, let's move on. Okay, so that was all technically review from last class. I know, but this is like a pretty complicated concept, so this is why we're going over it a couple times before moving on. But I do have one new concept for today, or actually two, but we'll start off with the inscribed angle theorem. So what is an inscribed angle? Well, an inscribed angle is formed by two lines in a circle that meet at a common point on the circumference. Okay, what does that mean? Well, let's take a look. So, two lines in a circle, and we see that here, right? This is number one line, this is line number two, and they meet at a common point down here, right? They meet at one point, and this point is on the circumference, which means it's on the edge of the circle, which means that the angle between these two lines is called an inscribed angle. So theta here is an inscribed angle because these two lines meet at the same point. Okay, so now what is the theorem for this inscribed angle? Well, the theorem states that an angle theta that's inscribed in the circle is half of the central angle 2 theta that subtends the same arc on the circle. Okay, that is a lot to process, so let's go over it a little bit. So the angle theta inscribed, we know what that is. That's just an inscribed angle, right? In a circle is half of the central angle 2 theta. So do you guys remember what a central angle is? We actually used this earlier. The central angle is just, it's close to an inscribed angle, but actually it's extended from the center of the circle, right? That's why it's called the central angle. So this purple angle is central, and this blue angle is inscribed. And this states that it subtends the same arc, which just means that this line crosses the same place as this line, or that this line, or like this angle, creates the same arc as this angle. Okay, so if I draw this out, if I follow this inscribed angle here, right, I get to this point, and I get to this point, and I can see that this creates this arc right here. And if I follow the central angle, so out here, we notice that it creates the same arc. And if it creates the same arc, then we say that it subtends the same arc. And that satisfies this theorem, which states that the central angle is 2 theta, which means that the central angle is just 2 times the inscribed angle. Okay, let's give an example. For example, if I have this inscribed angle here, and I have this central angle here, and I call this inscribed angle, for example, let's just say 20, right? According to this theorem, since they create the same arc on the end here, we know that this central angle is just 2 times 20, which is 40. So by knowing that this inscribed angle is something, we can immediately find what the central angle is, okay? So how would we actually use this? Well, here we have some problems. Number one, I'm given that this angle here is 180 degrees, and I'm asked to find what this angle down here is. So obviously we'll be using inscribed angles and central angles. First, I'm going to identify which one of these angles is inscribed and which one is central. So this one extends from the center, and this one extends from the edge. And remember, the edge one is inscribed angle, so I'm just going to put down IA for inscribed angle, and this one is for central angle, so CA. And the theorem states that the inscribed angle is half of the central angle, right? So if I know that the central angles is 180 degrees, then I know that the inscribed angle is half of that. So I divide this by 2, and that gets us 90 degrees. So now I know that this question mark can just be replaced by 90 degrees. Okay, does that make sense, everyone? It's just the relationship between this angle and this angle. Okay. Cool. So problem number 2. Here, I have another angle. Now, this looks a little bit weird because it's not exactly perfectly on top of each other, right? It's sort of slanted to the side. But actually, the theorem still stands because if we notice, this creates this arc, and this central angle creates the same arc. So we can still use the inscribed angle theorem. So the central angle is twice the amount of the inscribed angle. So I can say that if the inscribed angle is 70 degrees, then the central angle is twice that. So I multiply by 2, and I get 140. And vice versa, if I didn't know this 70, and I knew this 140 up here, if I knew the central angle was 140, all I could do is I could do 140 divided by 2, and that would give me 7 degrees, or 70 degrees down here. Okay. So, last one. What is this angle down here? Okay, now this shape looks really weird. So let's first try to identify which one is the central angle and which one is the... Oh, wow, we already got an answer. Okay, that's pretty good. Let's explain why it's 44. So we know that this inscribed angle is down here, right? Because this is the edge. And we know the central angle is here, right? Because it's in the center. And ignoring everything, ignoring all this weird stuff and all these weird lines, we already can state that the inscribed angle is just half of the central angle. And we know that the central angle is 88 degrees. Divide that by 2, we get 44. So good job, Jasper. Yes, it is 44. So cool. So that is the basics of the inscribed angle theorem. Now, let's actually put it to use. So here I have a problem, and I'm asked to find this question mark, which represents this arc length up here. Sorry, it's a little bit dark. I'm going to outline it again. So I'm asked to find the arc length. And the first thing we notice is that this inscribed angle actually creates this arc, right? So this arc is part of this inscribed angle. Now, remember, in order to find this arc here, we need to use one of these fractions, or two of these fractions, actually. And since we're trying to find the arc length, obviously, we're going to need the arc length, right? And the circumference. We need this fraction. And what else do we need? Do we need the sector area? Well, are we trying to find the area in any way? No, right? So we don't need this second part. Now, we actually have an angle here. Okay, we have one answer, 160 over 360, and I'll write that down for now. Let's see if this is correct. But going through the steps, we use this and we use this. So we need the central angle, it looks like, but all we have is this inscribed angle. So how do we find the central angle? Well, we have a theorem that gives us just that. If we have an inscribed angle, we know that the central angle, which is here, is just 2 times this. And what's 2 times 80? It's 160 degrees, right? So, yeah. So we know that this fraction is actually 160 degrees over 360 degrees. Okay, so you guys got the first step. That's perfect. Now, remember the goal is to find this arc length, right? I want the length, so somehow I have to transfer these angles over to the arc length. So how do we do that? Well, let's give it a radius first. Actually, I think that's enough for this problem. Honestly, I feel like if we dive too deep, it might get a little bit too complicated. So let's just give it this for now. So we have a new concept, the tangent lines. So these tangent lines are not to be confused with something that we use in trigonometry. If you guys were here a couple of weeks ago for our trigonometry class, you know, it's like something we used in triangles. When we have a right triangle and we have an angle, we can just find the fraction between two different sides of the triangle, right? And that's what we call a tangent. However, this tangent is completely different. In this tangent, the definition of it is a straight line that intersects a shape at only one point. So, pretty simple. If we have a circle here, we have a line, and this line is tangent only if it intersects at one point. And so obviously, this is a tangent line. Now, something like this line would not be tangent. Why? Because it intersects at 2 points, right? Something like this line wouldn't be tangent either because it doesn't intersect at all. So this line is the only tangent line. And the reason why I say the shape and not the circle is because it actually works for any shape. I could have like this squiggly line and then have a tangent line that intersects here at only one point. Or sorry, that was really badly drawn. But if it intersects at one point, I could still say that it's tangent. And we'll do some problems real quick. So here, I'll give you guys 1 minute, and I just want you guys to identify which one of these lines are tangent, right? So 1, 2, 3, 4, which ones are tangent? Okay, very good. 2 and 4. 2 and 4. Well, why? Because on here, we intersect at 2 points, not a tangent. Here, we intersect at 1 point. Yep. And here we don't intersect at all, so not a tangent. And then on this last one, we see that it only intersects at 1 point. Now, actually, if I extended this line, and here, if this came down also and intersected, then this actually wouldn't be a tangent line. So you do have to be careful when you're looking at shapes that go off the side, because if it does intersect somewhere else, then you would be wrong. But in this case, we can say that this is a tangent line. All right, let's move on and actually use this concept. So we have a theorem again, and this theorem states that a line tangent to any circle is perpendicular to the radius of that circle. Okay, what does that mean? Well, here I have a tangent line and intersects at 1 point, and this theorem states that the radius and the tangent line are perpendicular. So do you guys know what perpendicular means? Does anyone know the definition? Okay, perpendicular basically means that it forms a 90-degree angle, right? So super simple. If I have this line here and this line here, then we can say that these two lines are perpendicular because they form 90-degree angles, right? They're perfectly crossed. So we know that this tangent line is always perpendicular to the radius. And this works for any tangent line to the circle. For example, if I drew a line here, okay, I managed to draw a good one. And we draw a radius to the point where it intersects the circle. We know that this radius is always perpendicular to the tangent line, always forms a 90-degree angle. And that's very helpful later on. And we actually get to play with that later on. But for now, we have the second theorem. And the second theorem states that two tangent lines for any circle that meet at an external point have equal lengths. Okay, this one's a little bit more to process, but let's look at the diagram. Two tangent lines, and this is marked in green, so this tangent line and this tangent line that meet at an external point out here, so this purple dot, have equal lengths. And that's why I've put an X here and an X here, because I know that this tangent line and this tangent line are equal because they meet out here and they're both tangent to the same circle. Now, note that these tangent lines can often go off, like keep continuing on. But basically, when I say equal lengths, I'm only measuring by the point where they intersect to the radius. So it can go on this way too, but I'm only measuring where it intersects the radius, so this 90-degree angle here, all the way to the point where they intersect at an external point. And I'm counting this segment as x, right? So I know that that is equal to this section, which is also x. Okay, very cool. So let's work on some problems. So this first problem says determine if the following line A is tangent to the circle. So here is my tangent line, and I want you guys to try determining if it's tangent. So you guys might need to think back on what the definition of a tangent line is, but I'll give you guys 1 or 2 minutes to try to figure this out. Well, okay, Jasper asks, yes, is this a trick question? Well, yes and no. You'll see a lot of questions like when you get into class, like math class, or in your later years when you're taking tests and stuff, you'll see a lot of questions like this where you can't just rely on looking at the picture. So if I looked at this, it would look like, yeah, this is a tangent line because it only crosses at 1 point. However, we have to go back to the definition of a tangent line, right? So hint number 1, remember that a tangent line has to be perpendicular. So it has to be perpendicular to the radius, which means that this angle here has to be 90 degrees. Okay, now knowing this information, now can we determine if this is actually a tangent line or not? Okay, well, I'm going to go over this. And yes, it actually is sort of a trick question, only because when you look at it, it looks like a tangent line. But if we put it down onto paper and we actually try to do some calculations to find it, we'll actually find that this actually is not perpendicular. Why? Because, well, I have a triangle drawn out here, right? And we all know that in any triangle, these angles have to add up to 180 degrees, right? That's the definition of a triangle. All its angles add up to 180 degrees. So let's see if this angle is truly 90 degrees by trying to find this angle, right? So if I know that this angle is 63, and I know that this angle is 28, if I add these together, that gives me 91 degrees. And then in order to find this last one, since we know the area, or since we know the angle of all three combined, and we know these two, we can do 180, so this is the whole, minus 63 minus 28, which I found was 91. And this actually gives me 89, I believe. And that means that this angle actually is not 90 degrees. It is 89 degrees. And according to the definition of a tangent line, it must be 90 degrees. So this cannot be a tangent line, right? So yeah, very tricky, but you do have to be very careful when you're approaching questions like this, especially when it doesn't give you much information about the line, but it does give you like some other information. For example, these two angles. You immediately know that somehow you're going to have to use these angles to find the answer to the question. So don't just assume the answer by looking at it. Make sure you actually go back and check your work. Okay, let's move on. So we have tangent line theorems, problem 2. So here we're given that this segment AC right here is 9. Here, let me write that down, make it easier for us. And segment PB is 8. So I'll write that down too. So I have to determine the length of the line segment AB, right? So here to here. I'm trying to find this, so I'll give that X. So with this information, I can actually find the length of this tangent line. Now, the first step is obviously identifying that because it's a tangent line, this has to be 90 degrees, which means that we've actually formed a triangle, right? A right triangle. And I'll let you guys continue on from here, but let me just say that the main thing that we like to do with right triangles is either trigonometry, which we taught a couple weeks ago, or Pythag. Pythagorean theorem. I spelled that wrong. Theorem. And that basically says that c squared equals a squared plus b squared. So try using the Pythag to find out what AB is. And you might have to do one extra step, actually. I'll give you guys 1 or 2 minutes. Feel free to ask questions if you're stuck. Okay, if you're still working on it, no problem, but I'll just start off with the solution. So here, I said that we should use Pythag, And that happens when we have a right triangle, right? And with Pythag, we can find any one of these variables, C, A, or B. Or first, let's identify where it corresponds to. So if I have a right triangle, we know that this length is C, this length is A, and this length is B. And we know that C squared equals A squared plus B squared. So if we have any two of these, we can find the other one. So if I had C and I had A, I could find B. If I had B and A, I could find C. And if I had, for example, A and C, I could find B. Now, in this case, let's identify what we have. Well, for sure we have B, right? Because we're given it's 8. So B I can replace with 8. Now, this is a little bit weird because we don't have A, right? That's X we're trying to find out. So we don't know what A is, but it also looks like we don't know what C is because if this is the whole triangle going up to there, then we don't know this whole length because we only know that segment AC is 9. But what is this length? Well, it's actually very simple when you see it. We remember that any line going from the center of a circle to the edge of the circle is the radius, right? And any radius is the same length for a circle. That's the definition of a circle. And since we're given PB is 8, and we can see that PB is actually a radius, so we know that the radius is actually 8, then we also know that the length of CP right here is also a radius, which is 8. So knowing that these two are both radii, and knowing that this radius equals 8, we conclude that this radius also must be 8. And now we can find the length of this whole segment AP, and that's just 9 plus A, right? What's 9 plus 8? Well, that's 17. So we actually know C. C is 17. Okay, now we're ready to use Pythag because if we know any two of these variables, we can find the third one, right? And we know two of them. So let's plug in these. 17 is C, so we're going to put 17 squared. We don't know A, so we'll just leave A to be like this. And then B is 8, so I'm going to put down 8 squared. Okay, let's clear out some space over here. And I'll continue on this side. So let's solve this, right? I have 17 squared. What is 17 squared? Well, you could either use a calculator or do this by yourself. So I know that it's 7 times 7 is 49. I put the 4 up here. And then I do 1 times 7. That's 7 plus 4 is 11. So this is gone. And then I can do the second part. 1 times 7 is 7. 1 times 1 is 1. And then simple multiplication, you add these together. And you add these together. So 17 times 17 is 289. So we can write that down here. We know that that should equal A squared plus 8 squared. Now what's 8 squared? 8 times 8 is 64, right? So 64. Now we're trying to find A, so all we have to do is isolate A. So we come down here, we subtract 64 from both sides. So subtract it from here, that's gone. Subtract it from here, we get 289 minus 64. 289 minus 64, 9 minus 4 is 5, 8 minus 6 is 2, 2 minus 0 is 2. So we can put down A squared equals 225. And how do we solve something when we get A squared? Well, we just do the opposite of square, right? What's the opposite of the square? Well, the square root. So I take the square root, and this 2 cancel out. So I just get A equals the square root of 225. And the square root basically means what two numbers multiply together, or what number multiplied by itself equals the inside. And you could use a calculator for this, but for now, I'll just put it down. That's 25, because 25 times, or plus 25 equals 225. And so with this information, X should equal 25. Perfect. And I'll go on to the next problem. So for this, we have to determine the angle ADC between the tangent lines, so these two green lines, given that the angle ABC is 66. Okay, now let's mark this down. ABC from here to here to here, the angle in between that, so this orange angle here, right? This orange angle is 66. And we're trying to find this angle ADC. So from here to here to here, so this little blue line here. Now, how do we do that? Well, the first thing I notice is we have an inscribed angle, right? This is an inscribed angle because it touches the edge of the circle and it goes to 2 points and it creates an arc. Now, what can we do with an inscribed angle? Well, we can use a theorem that we were given, right? The inscribed angle theorem. And that states that the central angle that subtends the same arc, that creates the same arc, is 2 times the inscribed angle. So since we have an angle here, and we notice that it actually meets the same points as the inscribed angle, then this satisfies the theorem, which means that the central angle is actually 2 times 66. And then I'll do 2 times 66, multiply that down, 2 times 6, 12, carry on the 1. 2 times 6, 12, plus 1 is 132. So the angle here is 132. Okay, now from this, how do I find this? Well, it's a little bit more complicated than what we think. We actually have to split this up into 2 triangles. Now, if we don't immediately see that it should be a triangle, there's other ways to get to the conclusion, right? Because if we know that this is 132, and we know that these are tangent lines have to be perpendicular. So we have an angle here. We know that this is 90 degrees. We know that this is 90 degrees. Now, what can you do with 90 degrees and a given angle? Well, if you have a triangle and you're given 2 angles, you can always find the last angle, right? So I'm going to create a triangle by splitting this in half. And since I know that this is 90 degrees, and I know that this whole angle is 132, well, I actually know that if I split it in half, then that must be 132 divided by 2, because I split this angle in half, right? So I know that this angle on this side is 132 divided by 2, which is 66 degrees. And then I know that this angle on this side is also 66 degrees, because I split it right down the center. And now I have 2 angles of a triangle. So we know that these 2 angles have to add up, or these 3 angles have to add up to 180. So 180 degrees equals 66 plus 90 plus x. And I'm letting x be this angle down here. All right, so let's add these together. 66 plus 90 is 156. And then just write this back down. Isolate the x by subtracting 156 by both sides. X equals 180 minus 156. And that is, let's come down here and do a little bit of math, right? This should be 7 now, down here. And we get 24 degrees. So x is 24 degrees. Now that isn't actually our answer, because remember, we split this whole thing in half. We split this angle in half, which means that this angle is also split in half. So if we found half of it, then what is the whole thing? Well, the whole thing is just 24 times 2, right? 24 times 2. 2 times 4 is 8. 2 times 2 is 4. So this whole thing is 48 degrees. And that is our answer. Okay. So does anyone have any questions about that problem? It was basically a combination of everything that we use. Okay, a little bit confusing. Okay, let's redo this whole thing, but I'll simplify it, right? So first thing I used the inscribed angle theorem. Do you remember the inscribed angle theorem? Basically states that inscribed angle, IA, equals half of the central angle, right? CA. So like basically the central angle is 2 times the inscribed angle. And since I have an inscribed angle here, and I have a central angle here, and I know that this is 66 times 2, which we got as 132. So does that part make sense? Like getting angle APC out here? Okay, cool. Now, if we're given this, and we're trying to find this angle here, what I can do is I can split this in half, right? And the reason why I'm splitting this in half is because I'm creating 2 triangles. If you look closely, or let's look at the bottom triangle, it's more clear. If you tilt your head to the left a little bit, right? We have this, terrible line. We have a line in the middle, we have a line here, which is the radius, and we have our tangent line. And those three create a little triangle, right? And there's another triangle up here too. Okay. And basically, I know that this angle here that I just draw was 132 degrees. But because we know that this is 90 degrees, and we know that this is 90 degrees, we can say that in order to find this angle here, or I'll just draw it back on this normal image, this angle here is just 180 degrees minus 90 degrees minus whatever this is, right? Because we know that this angle plus this angle plus this angle has to be 180 degrees, right? So let's just say angle A plus angle P, or actually angle P represents this whole thing. And since I drew my triangle and I split this angle in half, I actually have half of P, right? So I have P divided by 2. So this angle plus this plus angle D, or half of angle D, because we also split that up in half, equals 180 degrees. So if we know that A is 90 degrees, since A has to be 90 degrees, because it's a tangent line, right? Tangent line has to form 90 degrees, or perpendicular. So A we can say is 90 degrees. P we can say, or is 132 degrees, but we need half of it. So 132 divided by 2 is 66. Plus half of D is 180 degrees. So earlier I did the math, right? I added these two together, subtracted these two from both sides onto here. So you got that D divided by 2 equals 180 minus this, which I believe was, let's just redo it. Or, this is 66, yep. Which I believe 156, 180 should be 24, yeah. And since we know that half of D is 24, then what is the whole D? Well, the whole D is 24 times 2, right? So that's 48 degrees. Okay. So now that I broke it down a little bit more, which part is the most confusing now? Is the central angle part okay? Is the triangle part okay as well? Okay, well, I hope so. All right. We have one last question, and I'll do this really quickly. So you guys don't really have to try to do this in your head, but it's just a sort of a proof of concept, proof that this tangent line theorem can actually be used. So I'm given quadrilateral ACEG. So this whole thing out here, where all of its sides are tangent to the circle. So we know that all of these lines are tangent lines. And we're given that D equals 2, DE equals 2, AC equals 9. Where's AC? AC equals 9, so this whole thing equals 9. FG equals 7. FG is 7. And AG is 12. AG, this whole thing, is 12. Okay, now there's a very specific theorem that we have to use. Going back a few slides, we learned that if two tangent lines meet at an external point, then those two tangent lines are actually equal length, right? So if FG and HG meet at the same point, then we know that FG equals HG, and we know that FG is 7, so HG also has to be 7. All right? See where we're getting there? Now, we can do this on another one, right? So we have DE, and we know that DE is a tangent line that meets at an external point with EF, which means that they have the same length. So EF must equal 2. Okay, well, that looks like everything we have so far. So now that we know that this whole thing, AG is 12, and we know that HG is 7, and they're on the same line, then what is AH? AH is just the remaining, right? So if I have a line, I know that the whole line is 12, and I know that this section is 7, then perfect, Jasper, 5, right? AH is 5. And now that we have this 5, guess what we can do? We can apply that theorem again. Tangent line, meet at the same external point, have to be equal lengths. This is also 5. There we go. And now, what is length CB? 4. Perfect. And now that we have this as 4, we know that CD is also 4. All right. Now we have all the measurements pointed out. And the goal is to find the perimeter. So remember, the perimeter is just the length of all the outsides. And does anyone want to add these up? I'll add them up on the side as well. Okay, well, if you're good, that's fine. It should be 32, if I did my math correct. But even if it's not, proof of concept we just were given 3 points or 4 points, and we had like 8, right? And with the tangent line theorem, we were actually able to find all of them. So that's just proof that the tangent line theorem is very useful. And yeah, so we are out of time today. We actually went a little bit over, so my bad on that. But as long as you guys understood everything, you guys are welcome to go. Or if you want, you can stay and ask some questions.